And so far they've focused on the vector space side, things you can sort of do with vector spaces like direct sum and how they translate to vector bundles, and how some don't translate as well to vector bundles, the more abelian category kernels and co-kernels. We're now going to focus more on the space side, or really the base space half of the structure of a vector bundle. And that's going to lead us to pullbacks. So, I mean, the first thing to note is that what I want to do is consider a vector bundle over some space. And the first thing you try is take a map from that space and you say, can I make a vector bundle over on the other space, right? And we have a map of vector bundles. That's a lot of data, but can we just take the data of a map of spaces? And, if it goes this way and I've got my vector bundle, then you'll see that there's no particularly good way to put a vector bundle structure on Y from F. So F star E. It doesn't work. So using a map of spaces, and we'll see similarly sections of vector bundles don't do well. They're not functorial. So this would basically say vector bundles aren't covariantly functorial, but they are contravariantly functorial. So, but if the vector bundle is over Y, or then I am going to make a pullback bundle. And let me just put that in a more general context of pullbacks in general. It's a categorical notion. It's pretty simple, but it's one of those things that, I don't know, I thought it was maybe kind of fancy because I hadn't heard about it in basic sort of grad school. So, so for a pullback, very general setup, I'm in a category, I've got maps from different objects into another, two different objects into another object, B to C, B and C into D. And the pullback is something equipped with maps. So that if there's anything else that is equipped with maps to B and C, there's a map which factors, and I get a map from the pullback, from that object to the pullback. So there exists a unique such factorization, making all of this diagram commute. So the pullback maps to B and C compatibly in composition to D. And if A maps to B and C compatibly in composition to D, then A maps to the pullback. So what are some examples? The two examples that you should start with, because pullbacks are just generalizations of two very familiar notions, namely intersection and Cartesian product. So if D is just a point, so these are examples in the category of sets. If D is just a point, and then B and C map to a point in the only way they can, then the pullback is B cross C. That's the universal space with a map to B and to C. If I map to B and C compatibly, then, there's no compatibility. Mapping to B and C is the same as mapping to the product. That's a familiar fact from sets. Another one is that if the maps here, let's just call them F and G. If F and G are inclusions, then the pullback is B intersect C, right? Because again, if I map to B and C and they're both subsets of D, the only way I can that could happen and get a commutative diagram is that I'm mapping to something in the intersection. And then in the category of sets in general, we have that the pullback. So in general, in the category of sets, the pullback is just a subset of the product, namely the collections of pairs, so that they map compatibly. Okay, so there isn't much to this. You know, there's some basic things. If you've never played with these counting categorical definitions, here's a little exercise. So exercise, compare, well, first compare with the general categorical definition of a limit. That's immediate. And then one thing about limits, show that the pullback is unique. So if you haven't played with these kind of categorical definitions before, that's worth doing. Okay. And then the main theorem, or the main construction we're going to talk about today is that, call it a proposition. And the proposition is that if I've got a vector bundle and I've got a map of spaces, oops, then the pullback, which I'm going to call F upper star of E, so it sits there. And by the way, what you do in the category of spaces is then just topologize the pullback as a subspace in the subspace topology of the product. This pullback is a vector bundle. And surprise, surprise, with fiber the same as the fiber of E. So I don't think I'm going to go in too much detail with this. This is pretty immediate. The fact that the preimage of any point is V is immediate from the definitions. If you want a local trivialization, well, the preimage of an open set in Y is open. So then you can see that the definitions allow you to trivialize the pullback. And then this is a map of vector bundles. And sometimes, you know, this is definitely, as I said, vector bundles are not the most useful category, but these pullback morphisms within the category of vector bundles tend to be the ones that we pay the most attention to. In that way, vector bundles are a contravariant functor, you would say. So a vector bundle, let's come back to that language in a bit. Okay, let me give you a couple more exercises then as we go along. One thing is, you know, what is the pullback of, say, the Mobius bundle under F from S1 to S1 multiplies by N. Okay, that shouldn't be too tough. Another one is, so if we have, show that pullback, formulate and show that pullback commutes with all of our algebraic endofunctors. They needed to be continuous, but on vector bundles arising from those. On vector spaces. So for example, that the pullback of a direct sum is the direct sum of the pullbacks. Should be. Again, some good things just to make sure you're following some of the definitions. Yeah, but let me then go to some of the main results. Well, first the non-results. So an algebraic topologist is going to be sometimes a little leery of garden variety pullback because, so in general, pullbacks are not homotopy invariant. And let's have our D is R2, and we can do B and C be two disks or 2 points. And then the pullback of that is, of course, the intersection, but any map from a disk to R2 is homotopic. So this would be homotopic to that, but the pullback, this pair of maps from B and C to R2 is homotopic to that pair of maps from B and C to R2, but the pullback is not homotopy equivalent to the pullback on the right-hand side. So you have to be careful with pullbacks, and there's a couple strategies, but one of the main ones is this gives rise to the notion of a fibration in general. So, but if either F or G is a fibration, then the pullback is the pullback sort of with respect to the other is going to be homotopy invariant. And we won't develop this language, but this is a way to preview something that, you get into more abstract homotopy theory. And then there's some categories where everything's a fibration in this way. And so, or maybe not everything's a fibration, but anyways, all pullbacks are good, but in sort of usual topology, pre-infinity topology, what one would do is try to look for fibration properties. And one thing that is stronger than a fibration is being a fiber bundle. And inside all fiber bundles are vector bundles. So in fact, it is the case. So the main thing I want to try to prove today is that if I have a vector bundle, I guess I'll continue just to say it sits over some y. And I've got two maps, and or really I've got a homotopy between them. Then actually I'll put over here, then the pullback of E is isomorphic to the pullback of E by G. So the pullback under F is isomorphic to the pullback under G. So I've got F and G, I've got this, the whole thing I'll call H or something like that. Well, great. So what's the idea? Well, I mean, obviously what we can do is we consider, this is our proposition or theorem, we can consider, it looks like cohomology, but I want the pullback of E under H. Sorry, I didn't, let me make this a little h, and then I think we'll all be fine. So this is a vector bundle over X cross I, and its restriction to X cross 0 is the pullback under F, and to the preimage of, or n to X cross 1 is the pullback under G. So it suffices to show that so any vector bundle over X cross I, for any vector bundle, the restrictions to all the X cross little t for t in the interval are isomorphic. Okay. And I'm going to, I'm just going to consider compact. This will be true for X compact or paracompact. I'll say in a moment, maybe I'll make it as an exercise. Maybe if the vector bundle is tame, there's an easier way to do this. I'm sort of, well, I don't really actually even know. Anyways, the argument I give must be, that I'll give must be standard, but it's not the one in Hatcher's notes. By the way, Hatcher has vector bundles, K-theory notes, and this is treated there. I couldn't find it immediately in Milner and Stasheff, by the way. Okay, so how do we prove this? So we're gonna, here, let X be compact, or even paracompact. And again, it should be, why is this not coming out? Sorry, no. That is weird. I wrote things between, there we go. Okay. I had to, the isomorphism between the board I'm writing on and the board you're seeing is not perfect. If you monitor the board, you'll have seen that as well. Okay. So let's prove this. And what I want to do is for any, we show that for any time t, there is an epsilon so that well, let's give the restrictions to X cross t, let's give that a name. Let's call that vector bundle sub t. So that the E sub s are all isomorphic for s in the interval between t minus epsilon and t plus epsilon. And I can arrange that to be open or closed, right? Because you can nest the closed interval with epsilon over 2 or nest an open interval. I think I want to choose the closed interval. And what this is going to do is, well, this is now this would give it because around any point I've got this in the interval, I've got this neighborhood where these are all isomorphic, but they overlap. So I take a finite cover of the interval, or a cover of the interval by these. There's a finite subcover which does the trick, and then I can compose these isomorphisms over the bands, and I get isomorphisms across the whole interval. So how is that going to work? So what I'm going to do, so this is my picture of x cross I. I'm now looking at x cross t. E sub interval, if you will, is a vector bundle. So there are trivializing neighborhoods for every point in x cross t. So let u alpha trivialize the vector bundle over this one x cross t. Of course, x is now compact, so finitely many suffice. This is, so then I'm going to, and what we can do is, and this is where we're going to get our interval now, we can take the, there's going to be some, so the projections, let's see. So these contain, so what finitely many suffice, call these ui for I equals 1 to m. The claim is basic point set topology. These contain some now I know, and that's what it's in my notes. Sorry. So even though we're in a product space, let's call this ui cross t minus delta t plus delta. Right, basis for the product topology. Trivialize. So now u alpha are over x. Finitely many of these suffice. I can just take then the minimum of the delta, and so then these. So we just consider let epsilon be the minimum of the delta. I, the delta I corresponds to the ui cross t minus delta I times t plus delta I. And then, and so now what we have is, let me just sort of draw it to the right here. Really now I just have a bunch of UIs in etc. My UIs look like this, and then I've just got the some epsilon neighborhood around it. But now over each of these strips, the bundle is trivial. Okay. So over each open set of the form UI cross from T minus, say 2 epsilon or whatever, 2 epsilon is minimum delta. And if I want, I can make it like this, T minus epsilon to T plus epsilon. For each one of those, the bundle is trivial. Well, a trivialization gives you an isomorphism between the two ends, and in fact gives you an isomorphism over all of the S in this interval, right? Trivial bundles are just immediately isomorphic to each other. The point is, though, so if I think about this little kind of product picture, the point is that, so this is UI cross this. I've got this way to think about its trivial sort of compatibly, and of course that gives me implied maps from this end to that end, and all those fibers are isomorphic. The point is, though, that if I've got some other uj and then some other ways of thinking about the fibers, in particular, if I've got some x here in the intersection, then those two maps over these two fibers are not going to be the same map. Almost surely they won't. They'll just be, everybody's trivial across. I've got some way to map this fiber to that fiber using the trivialization, but they won't be the same map. But then here's where a partition of unity comes in. So I'm going to let let me keep this picture up a little bit. So I take a partition of unity subordinate to this cover, and then I'm going to take, I mean, it's almost, it's kind of a pain to write out. I mean, so the starting isomorphisms on each UI, say between any two fibers, are going to be, I'm going to take are just, well, it's going to be yeah, notationally this is kind of a pain. Let me talk it through once. I've got this trivialization that means I've got a canonical map to the fiber, but that means to translate to that canonical map on the fibers, I have to go from the vector bundle, use the trivialization, apply the canonical map between fibers, and then use the inverse of the trivialization. Because let me make sure that my trivializations went from the vector bundle, or no, went from sorry, I looked this up and now Right. I think my trivializations went from vector bundle to the trivial bundles. So let's just go through it carefully so we can get it written down. So let's letting phi I be the map from E restricted to this UI cross T minus epsilon to T plus epsilon, to the same domain, UI cross the interval cross Rn. So those are our ends. Our partition of unity, I did plan for this, is going to be given by F's, not P's. Okay, so we have those trivializations. And then what will the maps on the two ends be? Well, we're going to have, so we consider E restricted to UI cross S versus E restricted to UI cross, well, we can make them all isomorphic to the one in the middle, say. And so I'm going to apply phi I, and then I'm going to project onto Rn, and then I'm going to, that's going to be the map, which gives me the, so we get a map of vector bundles. Over these slices, which by, well, let me actually just say by, well, so first I'm going to apply phi I. Now I can think of a product bundle. I'm just going to call this the map, the identification of restrictions of the trivial bundle. And then I'm going to take phi I inverse. And now this is a map between these two fibers that I just wrote. And great. But again, if we want to look back up here, this is just giving me the, the first isomorphism on UI. I have a different such isomorphism on UJ. I've got two different shades of red there. So what we can do, but now we have this map between fibers. So actually now take the magic of partitions of unity. So then take the sum of Fi. Let me let each of these be call it maybe like new I. These now are a way to kind of interpolate between my different isomorphisms. And what you need to do is check that these will give you an isomorphism. I was thinking that was immediate. I'm now worried that maybe this is why the proof isn't done this way. I'm worried that, of course, we can just take an R, take the identity map and minus the identity map, and then linear combination of those, half of one plus half of the other, will be singular. So I suppose this doesn't work. I might, well, I'm gonna stop there for now. I might end up re-recording this at some point. I'll leave it at that. Let me leave one other exercise other than trying to see if this proof can be fixed. Namely, let f from m to n be a map between manifolds. If of the same dimension, and E a rank D vector bundle over N, then compare the Euler number, Euler measure of E with that of F of the pullback of E. Okay, so that's another exercise. Yeah, I'm going to stop for now. I'm going to see if I can fix this proof, but I'll go ahead and keep this up for the moment. Might re-record later. And let me